So the wall correction, this is another topic, wall correction. Right. So here I am going to consider, let us say a coordinate system, let us call this S and N. N is the wall normal, S is a wall parallel coordinate system, okay, where I have a wall here. That means as I approach the wall, very close to the wall, I need some kind of a correction term, a damping function term here. And I want this damping function to be active in the range, let us say from y plus equal to 1 to about y plus about 200, okay. I want the damping function to be active in this part. That means it has to be automatic. As it is approaching the wall, the damping function, it's not like you have to explicitly model this or explicitly give a statement. If y plus is this, use this, and that is impossible in a generic flow problem. You will not even know what is the y plus value a priori. So it should be automatic. So it is approaching wall, the term should become active. As it goes away from the wall, its contribution should be nil. So what we do is wall correction for, first I am going to give for the wall normal component, okay. So for wall normal component, that is un prime square, here is the wall normal, right, wall normal stress. That means in this particular equation, for the wall normal stress equation, for this component, the pi nn slow. So the wall corrections will be there for both rapid and slow, okay. So that means the pi ij itself is modeled as rapid plus slow, plus it will have the wall correction for slow, wall correction for rapid term, okay, sum of many terms, okay. So I would call this prime here because it is a wall correction. So pi prime nn for the slow, this is minus 2 C1 prime rho epsilon by k un prime square f, simply modeled on the Reynolds stresses, because the slow terms are always depending on correlation of fluctuating quantities, not on the mean strain. So it is depending on here. So essentially what it is doing is it is taking away two parts in the wall normal. So wall normal, if you recall the two component limit, the wall normal you will have damping. I mean it damps faster than the wall parallel components, right, because of the pressure damping and viscous damping. So here pi nn prime, the wall correction is it is taking two parts away and this will be given one part each to the other. It is as simple as that, right. So this is your for the wall normal term, where f is the damping function, where the damping function f is k raised to 3 half divided by 2.55 xn epsilon. So xn is your savior. So if you see here, pi nn prime slow is a wall correction. That means it has to get active as you come closer to the wall, and this has f, and f is inversely proportional to xn. So as you approach xn, xn is the wall normal coordinate, right. So as you approach the wall, f will increase. So pi nn prime slow will be active. If you are going very far away from the wall, f will be so small that pi nn prime slow will be negligible. So it is a 1 over xn dependency, just like the wall dependency we introduce for epsilon boundary conditions and other places, damping functions. Okay, so this is one part here. F is the damping function here. Okay, so this takes care of only pi nn or the normal stress correction for the normal stress. We also need it for the parallel stress. Okay, there is one more thing I have to say here, where the damping function is this and xn is the wall normal distance. You don't have to implement this between this y plus 1 and y plus 200. All I am saying is damping function has to be active automatically. It is not like you need to go and explicitly say become active here. This is the zone of its influence. Okay. So now I need the other component for the wall parallel, which is US prime square, the two wall parallel stress components, right? Wall parallel for that equation, the correction term is pi SS slow prime, of course, is equal to, simply I am giving one part to each, taking two parts in the normal direction, giving one part equal to both. Okay. Yeah, just assume you have 3 kids at home, one the big kid, you are taking away some food from that guy and giving to 2 small children. That is what it is happening here. C1 prime rho epsilon by k un prime square f, one part each. Okay. Oh, sorry. One part each to the both. So you can write here that, note that 2 parts are taken, or you can say removed, from normal direction wall normal direction and given equally to the wall parallel direction, the S directions. So this will be for the normal stress, wall normal removed given to the wall parallel, but there is also a shear stress term. So we will see that correction for the wall for the shear stress also, that is for pi Sn prime, that is when you have US prime UN prime average term. So for the shear stress, equation, that is for your US prime UN prime equation. In that equation, the pi Sn prime slow is modeled as minus 3/2 C1 prime rho epsilon by k US prime UN prime f. Okay. So this gives the 3 correction terms that are used in the or the wall correction terms for the slow. normal stress, 3 normal stresses and the shear stresses. But we also need it for the rapid, okay. So the wall correction for rapid term. So here I would give out the expression, similar idea, taking 2 parts away and giving 1 part equally. The formula changes, okay, slightly, because we are not going to use Reynolds stresses, we are going to use the rapid term itself. So the pi nn prime rapid, okay, wall correction obviously is nothing but minus 2, this is the wall normal component, minus 2 C2 prime F pi nn rapid. So the pi nn rapid is being computed from your IP model. So minus 2 parts is taken away with the damping function of course, and the pi ss prime rapid, prime indicating wall correction terms. This will be C2 prime F pi nn rapid, sorry, pi ss rapid, okay, and the pi sn rapid term will take minus 3 half C2 prime the damping function and pi sn. So we are going to use the corresponding the rapid terms here for all the components. So this will complete your wall correction implementation for rapid and slow. So this is the sum total of, right. So note that, so if you are implementing the, let's say or I can say example here, example for pi 11 term model will be pi 11 rapid plus pi 11 slow plus pi 11 prime rapid plus pi 11 prime slow. With the wall corrections, four terms will be there for each of this equation. Okay, is this clear? Okay, so then the only thing that is left from implementing this model is the model constants. So we look into this, have model constants. So I have C1 which appeared in the rapid 1.8, C2 is 0.6, C1 prime is 0.5 and C2 prime is 0.3. Boundary condition here when we have this wall correction or resolving the wall flow is straightforward, right. Boundary condition is you are implementing the no slip for your velocities, dissipation rate like before you have options, epsilon you know how to implement boundary condition, and you have Reynolds stresses which has to go to 0 on the wall. So it is straightforward here, the boundary condition, okay. So the boundary conditions, if you can take a note here if you want. So the boundary conditions, this as well as this no slip here, right, no slip condition for the stresses, and epsilon you have options like EVM, you can have the near wall dependency introduced there, that we had like 1 over y square dependency introduced, you can use those boundary conditions here. We can also have wall functions if you are interested in not resolving the wall using Reynolds stresses, then wall functions are also an option. Okay. So there is a wall function derived for each of the stress here. Okay. So suppose if you are using wall functions, the grid guidelines are similar whether you do eddy viscosity model or Reynolds stress model. The wall functions and the wall correction, that means resolving, grid guidelines are same. So you need to have your first grid in the inertial sublayer for when you implement wall functions. So the linear and buffer layer are not resolved. So when you do wall functions, if you do this, then your u1 prime square is 3.67 u star square, your u2 prime square is 0.83 u star square, that is a wall friction velocity. u3 prime square is 2.17 u star square, and the shear stress u1 prime, u2 prime average will be minus u star square. If you have other components also, you can use the same expression. In many canonical flows, only one shear stress exists, like the turbulent channel flow or turbulent plane coed flow that you did. The other two components, I mean by theory you cannot say that, only after doing the experiments or DNS you can realize that the other two are negligible or zero. Only this primary shear stress exists. And epsilon, of course, you need a wall function for that, which is same as before, u star cube by kappa y. So u star is your wall friction velocity, kappa is the wall the von Karman constant, y is your wall normal coordinate, of course. Y or xn, if xn is the one you are using, depending on what you want to call it. Is this clear? The Reynolds stress modeling part. Okay. So there is instead of solving a transport equation for Reynolds stresses, some would like to go ahead with using, let's say, an algebraic expression, like the we had a zero equation model, right, for eddy viscosity also. Like that, instead of having a transport equation for Reynolds stresses, how about having algebraic expression for Reynolds stresses? This is called ASM, algebraic stress models or algebraic Reynolds stress models. I will not go much deeper into it because these are not very popular, but this option exists in, I think, in one or two commercial codes they exist, but they are not very popular. I will just give you the model philosophy. How do they, why did they thought about it and what is the idea behind it? Just an introduction to that one. Algebraic stress models, the so-called ASM, algebraic implying algebraic expression here. So what they do here is that there is a model assumption that the transport of the Reynolds stresses is related to the transport of the turbulence kinetic energy. Transport implying the convective transport or the advective transport and the diffusive transport. The two convection diffusion of your Reynolds stresses is related to convection diffusion of turbulence kinetic energy. That's the assumption. Okay. So the model assumption here is that the model assumption is transport, that is convection and diffusion of Reynolds stresses is related, or you can express it in terms of transport of your turbulence kinetic energy. This is a model assumption here. So that means this essentially implies that symbolically I am writing Cij is your convective transport term in a Reynolds stress equation minus Dij. So I will write it here, the convection part, the diffusion part. Okay. So Cij minus Dij, we want it to be proportional to Ck or Ctke minus dk, transport here, right. So Ck comma dk term, or I can write this as Cij minus Dij is equal to Ck minus dk and introduce the Reynolds stresses here, because the whole point is to get an expression for Reynolds stress. What is the point of relating the convection diffusion of this to the convection diffusion of that? I need an algebraic equation for Reynolds stresses. So I am introducing that here, ui prime uj prime by k, non-dimensional. So therefore I can get, so now I can express this Cij Dij as what it is related to on the right hand side of those equations, right. However, Cij minus Dij, what is this related to on its right hand side? I have Pij, production rate term, I have pi ij term, and then epsilon ij, and Ck minus dk term is equal to Pk minus epsilon. So therefore I can say that Pij plus pi ij minus epsilon ij is equal to ui prime uj prime average by k Pk minus epsilon. So this is your algebraic expression. So each Reynolds stress you can obtain using some model for each of these terms. I am just giving the idea behind algebraic stress model, would not like to go deeper into this one. RSM is much more popular than ASMs, Reynolds stress models, or solving transport equation. If you are able to get converged solutions, that is popular. But in the so now we can say that I am more or less completing the statistical approach in the modeling, right. So statistical modeling had Ran's equation, solving Ran's equation. That means we are interested in mean velocity and mean pressure. To get that, we are modeling the turbulent terms. We are lumping it as Reynolds stresses, and Reynolds stresses are either modeled using a d-viscosity approach or solving transport equations for it. But the main objective is to get mean velocities and pressure. If that is your focus, that is a focus for industry, this is sufficient. Of course, you have to live with some error there. But beyond that, if you want to capture turbulence, I am not going to model these correlation terms as lumping it as some statistical equivalent. Instead of that, I would like to let the mesh capture the random or stochastic component. Then we move into what is called the eddy resolved methods. In the next class, I would start that part.